Hi everybody. In this video we're going to be talking about the type of differential equations that describe harmonic motion. This is the motion of things moving back and forth. All right, so where do you see harmonic motion? Well, one way that you can find it is by doing a pendulum. So you just put something at a pivot point and let gravity do the work, right? It'll rock back and forth. That's a pendulum. And that's called harmonic motion, this back and forth motion. Also, where you'd see it is with a spring. If you attach something to a spring and stretched it, let go, it'll just oscillate back and forth. It's also very important in describing the properties of waves. So we know that waves have a back and forth nature to them. Compression waves, sound waves, do the same thing, but in a kind of a more of a back and forth, in and out kind of behavior. So these are very important things to study. And so let's take a look at how this arises in differential equations. Okay, let's go down to the paper. And the type of differential equations that we're dealing with have a name. They're called autonomous differential equations. Autonomous differential equations. And autonomous differential equations have the form y double prime equals a function of y and y prime. So these are second order differential equations, right? Because there's two derivatives, second order. And this means that on the right-hand side of the equal sign, we're going to have an expression involving y and y prime. But what's important is that we don't see any t's here. So what I'm thinking of, we're describing the motion of things. So we're thinking of t, time, as our independent variable, and not x. Let's think of it as t for this presentation. But the important thing here is that you don't see it here, right? T is not appearing. It's just y and y prime. Okay. So if you can write it in this form, that makes it autonomous. Well, what are one of the things we can do to simplify a differential equation? Because, for instance, maybe I don't like the fact that this is second order. Is there a way I can reduce it to maybe first order? Well, make a substitution, right? So what I'm going to do here is I'm going to let v be y prime. And if I do that, then v prime is going to be y double prime. And what that's going to allow me to do is rewrite this as v prime is a function of y and v. Okay, so great. Now it's a first order differential equation. Problem is I've introduced this new function v that we have to deal with. And what we're going to do is we're going to think of v as a function of y. Okay? So if I think of v as a function of y, then how do I relate that to v prime? Well, this is the derivative with respect to t, right? So how do I get those both into the works? Well, it comes from the chain rule. All right? The chain rule tells us that v prime, the derivative with respect to t, is the derivative with respect to y multiplied by the derivative of y with respect to t. Okay, in other words, it's equal to dv dy times y prime. That's what we're calling y prime. So that's what I'm just going to write here. But y prime, actually, I'm going to write a v because that's what we're letting equal y prime. Okay? And so let's take one more step here. I'm going to replace v prime with this. Okay? So we're going to have dv dy times v is a function of y and v. Okay? So we are often going to take our differential equation and put it into this form. Okay? And this is something you can always do with an autonomous differential equation. Now, the next thing that I want to talk about here, and this is a really awesome thing that you can do with these, and it's called the phase plane. Okay? So we're going to take a look at the phase plane. The phase plane is a set of coordinates where we let y be the horizontal coordinate and v be the vertical coordinate. Okay? And what we're going to do is we're going to study how solutions plot in the phase plane. Okay, so you might get a solution to our differential equation might end up looking something like this. Okay, that's a solution curve. Now, any point on this curve is going to represent the state of our solution at some time. Okay, so this point over here is going to be the point y of t, comma v of t. Now, what are we looking at here? Well, y might represent the position of the object. Right? So if we have an object on a spring, it's the position of where that is. If I let go, it's going to move around. But where is it at any time? Well, that's going to be represented by y. Now, what's v? Well, remember, v is y prime, the derivative of y with respect to t. So v is the velocity. So now we know why we chose the letter v here. So we have the position and the velocity. That's what this is plotting. So any point is giving us both the position and the velocity of the object at any time. And that's determined by its position in the phase plane. All right, so we're looking at position versus velocity. And as things move around here, their position and velocity are changing simultaneously. Okay, we can tell what they are just by reading off the coordinates. This curve, when we trace out a solution curve to this in the phase plane, this is called a trajectory. Oops, let me try spelling that again. Trajectory. So the curves in the phase plane that solve the differential equation are called trajectories. And not everything plots as a curve like this. You might find some solutions that just live as points. For instance, imagine if I didn't stretch the spring at all, if I just left it in its natural position. What's going to happen? Well, nothing's going to happen. It's not going to move, right? It's only going to move if I stretch it and let go, and then it'll start wiggling around. But if I just leave it where it is, it's not going to go anywhere. Now, its position will have some value, but its velocity will be 0. And so I'm going to have some position on the y-axis, and it's just going to be some point. And that is the trajectory. It just exists as that point. It's not moving anywhere. Okay? And if we have such a behavior, that's called an equilibrium. Right? So the equilibria are the points on the y-axis that are solutions to this. So it's like a trajectory, it's a curve, but it's all compressed down and it just stays as one point. Okay? So these are the kinds of behaviors we're going to be looking at. Now we're going to actually look at things in a little bit of a special case here. So not only are we going to look at autonomous differential equations, we're going to assume that they have an even more particular form, okay, just to make things easier for us. So just to get things started, we're going to say we will focus on the autonomous differential equations of the form, and it's going to be y double prime plus a function of y and y prime times y prime plus p of y equals 0. So this is a special case of this, right? If I move all of this stuff over to the right-hand side, if I subtract it from both sides, I will have something in the form that we talked about before, okay? And if it's of this form, if I apply that v procedure to this, well, y double prime becomes v dv dy. This becomes q of y and v times v, and then we have p of y equals 0. So we've gone into the phase plane picture here, where we're looking at things in terms of y and v, position and velocity. Okay? All right. So let's look at our first example. Okay, so our first example is going to be where Q is equal to 0, right? We're going to take this Q here, and we're just going to set it equal to 0. So we're just going to have this, or this. Okay? That's example 1. Q is identically 0. Remember, we use 3 lines to mean it's 0 for all time, right? For all values. Right? So we're just looking at the differential equation y double prime plus p of y equals 0. Okay? Well, go to the phase plane picture. So y double prime becomes v dv dy. Okay? And now, what we're going to do is we're going to anti-differentiate both sides. Okay? So what's the antiderivative of this? Now, what we're going to do, I should have specified, with respect to what? And that's a question you should always ask. Derivative with respect to what? Antiderivative with respect to what? With respect to y. Okay? So anti-differentiate everything with respect to y. Okay? Well, here we have v times dv dy. The antiderivative, 1/2 v squared. Okay? If I differentiate this with respect to y, this is exactly what I get using the chain rule. Right? Now, this is going to be something. I don't know what function little p is, so I can't tell you exactly what it is, but I know it's going to be some new function of y. I'm going to call it, as is usually the convention when we anti-differentiate things, we use a capital letter. So if that was a lowercase p, the antiderivative is going to be an uppercase p. And the antiderivative of 0 is just a constant. Okay? So now we have this. All right. Now, one thing that we can think about when we're moving objects in space is we can think about their mass. Okay? So if I suppose m is the mass. I'll just leave it like that. M is mass. Oops, I'm kind of blocking the way there. M is mass. All right? So we're going to multiply through by m. Okay? So I'm going to have 1/2 mv squared. And you physics people should be thinking, oh, I've seen that before. Okay? Now, physics people, what is this? That's kinetic energy. 1/2 mass times velocity squared. That's the formula for kinetic energy. So what we have here is we have kinetic energy, the energy that has to do with the motion of something. Okay? What is this? This is going to be potential energy. Potential energy. And what is on the right-hand side? Well, it's a constant. Right? This is a constant. Okay? So let me just take a moment to describe what potential energy and kinetic energy are. Okay? So when I take an object like this pen, okay, and I lift it up, okay, I am storing potential energy into this object. That it now has the potential to do stuff, right? If I let go of it, it's going to fall. That potential energy that I stored into the pen, transferred it from myself, my muscles, and my body, transferred that I did work to move this pen upwards. It now has potential energy. When I let go, that potential energy begins to transfer into kinetic energy, and it falls. Kinetic energy is the energy of motion. And as it falls, it has less potential energy. It can fall less now, right? Because it's moving downwards. It's spending that potential energy, transferring it into kinetic energy, motion. And all the while, what's happening, according to our equation here, is that the sum of those two things is staying a constant. So first, when I lifted up the pen, it's all potential energy. Kinetic energy is 0 because it's not moving. When I let go, the potential energy begins to decrease, the kinetic energy begins to increase, but at all times it equals a constant. And the fact that it's always equal to the same constant, that's saying that energy is conserved. You can transform potential to kinetic, but the sum total is always the same. Unless we introduce new energy into the system. If I go and lift it up again, I'm imparting new energy into a system. So we're thinking of a closed system here. But the point here is that this equation here is called conservation of energy. Conservation of energy. Energy is conserved. The sum of these two things is always equal to the same constant. All right, so that's a really cool property that just comes out of the differential equation here. Now, what does this look like in the phase plane? Okay, so we have the position. Let's just think about the pen. When I lift up the pen, I am setting its position to be some non-zero amount. Okay, so it's starting at some position, and I'm holding it so its velocity is 0. Okay, so what's going to happen when I release it? The position starts to decrease. Right? The height goes down, but the velocity goes up. So what happens is this moves through phase space along this trajectory. And if this is where my table was, its height is now 0, right? And its velocity is substantial. The velocity has become something positive. Now, the moment it hits the table, now its velocity instantaneously drops to 0, and that's a discontinuity in this graph. We won't consider that. We'll just go up to the point where it hits the table and just think about that. We get this nice curve. This is the trajectory through the phase plane of dropping a pen. This is what it would look like. Okay, so let's look at an example of something else. How about a spring? Okay, so what we're going to do is we're going to look at what they call an undamped spring. Damping is what happens when you have a force that depends on your velocity. And so a good example of this is wind resistance. Okay, the faster you go, the more you feel the effect of the wind. And so wind or air resistance it's related to your velocity. Okay, so and that's why when things fall through our atmosphere, they actually achieve what they call a terminal velocity, because that wind resistance, it actually becomes strong enough to overcome the force of gravity, right? And so if we have something like that, if we have a function, if we have a force that's a function of velocity, then we would have a damped system. To say it's undamped means we're neglecting wind resistance, okay? So we're not thinking about wind resistance here. And what we're going to do, though, is we're going to imagine a spring. So here's a slashed out area just represents like a wall, all right, an impenetrable barrier. And I'm going to attach a spring to that wall. And I'm going to have a mass on that spring, okay? And so I'm just going to draw a box. Now I'm going to draw it in a dashed line because this isn't where the mass is going to be, really. I'm going to take that mass and I'm going to pull it down. All right, so I'm going to take that and just drag it down a little bit more. All right, so I'm actually going to pull it down to here. So we have a mass m. This is where it wants to be. This is where I pulled it to. Okay, so this is the initial position, but this is where it's comfortable. All right, and so I'm going to have a y-axis here, and where it's comfortable is we're going to call that y equals 0. Okay, and what I did is I pulled it down to some initial value of y, and I'm going to let go, and I'm going to see what happens. Now, we know what's going to happen, right? We know that when I let go of the spring, it's supposed to oscillate up and down. So that's what we should get. But let's think about what is going on. How can we describe the differential equation that's telling us what's going on? Well, we're going to have the acceleration of this object. Okay, so we have this acceleration of this as it's moving along, and we know that mass times acceleration is a force. Okay, so I'm going to write that down. Mass times the acceleration, and acceleration is the second derivative of its height. Y is representing height here. We also know that the spring exerts a force. Okay, the spring exerts a force, and I know that the further I pull that spring, the harder it is to pull more, right? The further I go, the harder it gets. So the force seems to be proportional to how far I've pulled it. And so we have a constant times the distance that I've pulled it. But if y is in the up direction, right, y is the height, the spring is pulling against the position of the object, right? If I drag down from here, the spring is actually pulling in the opposite direction, right? So we actually have a negative here, okay? And in particular, if I'm below 0, this force is actually pulling up. So if y was negative, this negative sign is important. We need it there to make sure this force is positive, pulling in the opposite direction. Okay, so what we're going to do is we're going to put this in the phase plane picture. And so we know that y double prime becomes dv dy times v. And okay. And now what did we do before? We anti-differentiated. Now we said what this becomes, right? That becomes 1/2 v squared. So we have, we end up with 1/2 mv squared when I anti-differentiate the left-hand side. What happens when I anti-differentiate the right-hand side? Well, I get minus k over 2 y squared plus a constant. Well, here's my kinetic energy again, right? Let's collect these terms on the left-hand side. 1/2 mv squared plus k over 2 y squared equals our constant. This is, again, this is the kinetic energy, the energy having to do with the motion of the object. This is my potential energy, the energy that you're storing when you stretch that spring. It's supplying that potential energy, right? Now, what we said was that the sum of kinetic plus potential, this is the total amount of energy. So what C is representing is the total energy. So let me just call that E. I may as well just not call that C. Let's just call it E. All right? So here we have an equation. Now that's an equation that you know how to graph if we're looking in the phase plane. So pause the video, think about what the graph of this is going to look like. Okay. And we'll count down 3, 2, 1. You should have realized this is the equation of an ellipse. All right? So if you plot this, you'll get an ellipse. Now, that's a it's a lumpy ellipse, but imagine I drew it nicely. How is the motion actually exhibited on this ellipse? Well, what did we do? We started by pulling this mass down to y0. Where's y0 in this picture? Well, it's a negative value for y. I pull down the mass. I'm going to hold it there and then let go. So the velocity is 0. So I must be right here. Okay, that's my initial position. Y0, 0. Now, what happens when I let go? When I let go, the spring is pulling up. That potential energy is going to get released and turn into kinetic energy. So this is going to go up, right? So y is going to increase, and the velocity is going to increase. So the velocity becomes positive. So I go this way. Well, the mass goes this way. I'm imagining myself on the spring. I guess I haven't gotten out much these days. So let's we go around this ellipse, right? And we travel around. Eventually we get to here. What's that? That's the highest value of y. We'll get up to here, but now the spring is pushing back the other direction, right? So now it's going to so now it's going to push back this way, all right? So now the spring is pushing back down. It's going to come back down. So we're going past this point, and we're coming around this way. And then what happens? We get back to the bottom where we started, and we're back to here, but now the spring's pulling back up again. So we're going to loop around. So we just keep going around and around this ellipse forever, right? If there's no wind resistance, no friction or anything like that, this would just oscillate forever, and that means to just spin around this ellipse in the phase plane. And that's where this phase plane gives a really beautiful picture of what's going on. Harmonic motion, the motion of just oscillating back and forth, is going around some shape. It's actually a closed curve in this case. It's not always going to be a closed curve, but in this particular differential equation, it is. Now, what would happen if I just left the mass right here? If I didn't pull it down at all, I don't even touch it, I just leave it dangling. Well, the position is 0, and it's not going to have any velocity. There's no reason for it to move, so my equilibrium point is right here. Okay, so I have this equilibrium point in the center, representing no motion. If I pull it a little bit out, I get an ellipse, and it'll spin around and oscillate a little bit less. If I pull it farther, I get a bigger ellipse. Right? So depending on how much energy I store into the system, I get a different size ellipse. And that energy is right here. So you can see the energy in the system. It's directly related to the size of the ellipse that we're going around. Right? And it would be fun to think about. You might think about this on your own. If these things so happen to just make a perfect circle, how does the energy relate to the radius of that circle? That's an interesting thing to ponder. Okay, so let's do another example. We're going to look at a pendulum, as I said I pointed out that example. So let's look at it.